Now that we know that the graph hits a local minimum or maximum when the derivative is equal to 0, we can use that to help us solve optimization problems, where we're looking for that optimal point to minimize something bad, like an expense, or to maximize something good, like revenue. So let's look at several optimization problems in this section. We're going to start with the classic fence problem. The key to these optimization problems is we need to remember that the critical points, or where the derivative with respect to x is equal to 0, is where the minimum or the maximum will occur. So let's say a farmer has 300 feet of fence to make a rectangular area with 5 long sections. In other words, we're going to build a fence here. And in it, we're going to go 1, 2, 3, 4, 5 long sections within the fence. We want to know what dimensions of the fence will maximize the area. Well, let's take a look at what we know about this fence. The fence is going to have some height. Let's call it x, and some length. We'll call that y. What's nice then is all of these vertical lengths are all going to be x all the way across, which means there's a total of 1, 2, 3, 4, 5, 6 x's. And the y on the bottom is going to match the y on the top if it's a rectangle. So in addition to the 6 x's, there's also 2 y's. All of that fencing together is going to equal the 300 feet of fencing that we have available to us. But we want to maximize the area. The area of a rectangle is base times height, or in this case, x times y. X times y is what we want to maximize, but the problem is it has 2 variables in it, and we want to work with just 1 variable. So we're going to use this equation on the left to solve for one of the variables. Let's solve for y. We can solve for y by subtracting 6x from both sides, and then we get 2y equals 300 minus 6x. And then we can divide each term by 2 to get y is equal to 150 minus 3x. So I can take this 150 minus 3x and replace the y with that 150 minus 3x. And that gives me x times 150 minus 3x. That is what we want to maximize. And we know that maximum is going to occur when the derivative is equal to 0. Before we take the derivative, though, we're going to distribute the x through to make this easier. It's going to be 150x minus 3x squared. And then we can take the derivative of this and set that derivative equal to 0. Well, the derivative with respect to x is equal to 150 minus 6x. If I set that derivative equal to 0, that's going to be my critical point. Adding 6x to both sides gives me 150 equals 6x. And dividing both sides by 6 tells me that x is equal to 25. I know the height of this fence is going to be 25. The length comes from the y, which we can get by plugging in the x value we now know. Y is equal to 150 minus 3x, or 3 times 25. Y is equal to 150 minus 75, so y is 75. If I want to maximize the area with this 300 feet of fencing, we have to do a 25 by 75 foot fence. That is one example of an optimization problem where we set the derivative of what we want to maximize to 0 and solve for our variable. Our next video is going to take a look at another context where we can do the exact same thing to optimize a situation.